this basic example of torsion, we've got a solid shaft that is 18 foot long, has a 4-foot kip torque being applied at its end. The material is a steel tool alloy L2. It has its yield stress of 51 ksi. Its modulus of rigidity, or also sometimes called the shear modulus, is 11,000 ksi. Here are the critical equations that we derived earlier for torsion, expressing Hooke's law for elastic behavior in torsion. Tau equals G times gamma. The shear stress at any distance rho from the center of the cross section, or tau equals T rho over J. J is the polar moment of inertia, and then the angle of twist in that section when T, J, and G are constant along the length is phi equals TL over JG. On our equation reference card here, that's on the back of the first page, or page 2. And so same things, all of this stuff right here is the applicable portions for us in terms of our models. Right? Now on this one, since we have constant torque, you really don't need the torque diagram, but we're going to use it here when we to help illustrate how we do this in non-uniform torque or other non-uniform situations. And so we'll show then the system with the fixed end at the left. Remember, we're using the right hand rule, so the fingers go in the direction of the torque, and the thumb then tells us what direction we're going to draw this double-headed torque arrow. And remember that positive is along the outward normal, so this 4-foot kip torque is in reality, when we go and draw the torque diagram, going to be a negative value. And again, since this is a constant all the way along its length, then we can just show this like so. And negative because of our positive sign convention. And there's your minus 4-foot kip in your torque diagram, illustrating very clearly to us that we have constant internal torque all the way along the length of this member. Now, must determine the magnitude and location of the maximum shear stress, noting that tau equals T rho over J. That gives us tau as any function of rho. Of course, tau max is going to happen at that outer fiber. So tau max is going to be equal to this max combination of all of these pieces. In this case, since the torque is constant, the J is constant, then this is going to be right at rho equal to C, that outer radius, and so we'll have TC over J. Right, and that's TC over, and then J being for a solid cylinder would be pi over 2 times the radius to the 4th power, right? And so that would simplify to T over 2T over pi C cubed. I've taken the 2 up to the numerator. Now let's substitute everything in, keeping track very carefully of units. 2 times 4 kip feet of torque over pi, and then our radius is 2 inches, not 4 inches, but 2 inches cubed. And that would be kip feet over inch cubed. That's a little odd, so let's convert the feet into inches. Well, let's do that conversion correctly, huh? 12 inches over 1 foot. There we go. That might make a little bit more sense. And so we're going to get then 2 times 4 times 12 divided by pi divided by 2 cubed, which is 8, and that will be then 3.82 ksi. That's much less than tau y 51 ksi, so we are in the elastic region, so all of our models are valid, and we have then a correct model for the max shear stress on the cross section. Right, then we're asked to determine the angle of twist of the free end with respect to the fixed end. And we have constant everything here, constant T, constant J, constant G, all of that all the way along this length, so it's just a straightforward application of our model. Phi equals TL over JG. And away we go. We've got 4 foot kip that we will convert into kip inches. And then we have 18 feet, so we'll convert that also into inches. So now in the numerator we have kip feet, or rather kip inches squared, over our j, which is pi over 2 inches to the 4th, times g, which is 11,000 kips per square inches. So we have kip inch squared in the numerator, and we have kip inch squared in the denominator, so that's going to be unitless. So we're going to get an answer in radians. So let's see, 4 times 12 times 18 times 12 times this 1/2 that goes to the top, then divided by pi, divided by 2 to the 4th, which is 16, and divided by 11,000, and we have our answer here of radians of 0.0375. Now there's one thing I didn't do, and that was keep track of units here, right? So positive sign convention would have been right hand going this way, curl in that direction, but we've got the opposite. That's why we have a minus there. So there should have been a minus there and a minus there for our sign convention, and there's your answer for the various requested quantities on this item.